In this first series of lectures in our class GS 240 Data Science for Geoscience, we'll be covering extreme value statistics. I think this is a very interesting part of statistics that actually has a number of applications in geosciences, and it's not typically part of the curricula of data science methods. The first presentation will mostly be looking at introducing the nature of extreme value statistics and some examples, cases that apply to the geosciences. There are a number of superb publications for that. I think the book by Coles, An Introduction to Statistics Modeling of Extreme Values, is quite good. It's somewhat mathematical, probably not a really an introduction book, but it's a good reference. But I do like often our papers written in the topic, particular papers in subject areas, because these are also great ways of introducing extreme value statistics by example, which is something that's nicer for you, for students in general, to look at. There's a number of papers that we will be looking into. One is related to volcanoes, and one is related to diamond sizes. First of all, I'd like to clarify a little bit nomenclature here. When we talk about extreme values, we have to be careful in not equating that to outliers or let's say anomalies. There are many names that are being used for sample values that are somewhat high or extremely high or possibly extremely low, depending on the kind of problem you're looking at. An outlier is basically a sample that needs to be removed from the data set because it's not part of the population we're trying to study. And so that brings us to what is part of the population, evidently. And so, in fact, extreme value statistics is a way to detect that, because if you have a single very high value, it's hard to tell whether it's an outlier, meaning not part of the population, or it's an extreme value, which is essentially part of the population. It just occurs very rarely. So why do we need topics such as extreme value statistics in this particular course? Well, much of your current knowledge relies a lot on fitting of distributions, whether these are parametric distributions or non-parametric distributions. So we obtain some sample data. We can fit a normal distribution simply by calculating the arithmetic mean and calculating the empirical standard deviation, equating that to the population mean and population standard deviation, and we have a fitted distribution. So that can also be done for non-parametric type models such as kernel density estimation. So most of what we're doing there is related on a principle that's called the excentral limit theorem. That's something related to typically has to done with averages. So we'll have to be mindful in applying some of these techniques to extreme values, and I'll give a few examples of that as well. So there's two motivating examples that I will be discussing in the overview. That will later on also talk about rainfall, which is another interesting extreme value event. And so that will come more in when explaining the various methods. So the first example is something that I'm quite familiar with, since this was actually my PhD topic, is the valuation of diamond deposits. So a little bit of background here. So diamonds occur either in their natural context, which is Kimberlites. These are basically volcano eruptions or magmas that have come up very fast from the mantle, where diamonds are frozen into their particular thermodynamic state and basically form at that particular depth and temperature, which is very deep, and they get frozen into that state. So these volcanoes are then eroded through rivers, whatever we may have, and so we get what are called placer deposits. So we can have placer deposits that are rivers, but it can also have placer deposits that are beaches. And Namibia is a good example of the latter one. So mining diamonds is very expensive simply because they are rare events, particularly the commercial diamonds. There are actually a quite substantial number of diamonds in a sample or in an excavated block. It's just that many of them are very small and will never be found, or we are just not interested in them. So that also means that diamonds require these huge volumes to be mined. And so if you're going to evaluate a diamond deposit simply by drilling, or by excavating small volumes, then at best you're going to find only a few thousand stones. And so it's also then very common that in those few thousand stones you have only a few that are actually of significant value or size. And that's another problem that we need to deal with diamonds, is that there's a difference between size and value. Unlike, of course, gold. Gold has a certain unit price. Diamonds do not, because their value depends on their properties such as the color, the inclusions, the clarity of the diamond, etc. So we can ask ourselves a few interesting geological questions. If I look at the size distribution, that means I have a collection of stones, and I look at size distribution between Kimberlites versus fluvial and beach deposits, would we see a difference? And so that's an interesting question. Geologically speaking, we would see a difference, because the Kimberlites have the stones that are essentially non-eroded. So even diamonds are hard, they tend to get filtered through the system. And this filtering creates different diamond size distributions. But are these size distributions of different types, or are they just parametric differences? Similarly, do all kimberlite deposits have similar size distribution, and what would that essentially mean? And so a third question could be interesting, could be, is this statistical difference that I see, is that related to the process of formation and the transportation? So can I reveal what kind of process essentially can be deduced from the stone distribution? And this is very typical for geological forensic work, is that we're going to try to find indicators for something that's a difference. Whether we're looking at isotopes or diamond size distribution or size distributions, or relations between isotopes, they're all indicators of some process that has occurred. And so we'd like to get more insight into this process. So then we have to think about, to what extent does the statistical distribution reflect a process, or to what extent does a process influence the nature of the statistical distribution? So size distribution have general and more general application than just diamonds, obviously. Sizes of craters, sand grains, the length of faults, the size of galaxies. So these are all types of size distribution. The magnitude of an earthquake, they're all size distributions. And so what are the common size distributions? And can I come up with some expressions for that? So what you probably already have in mind in terms of size distribution is the log-normal distribution. So the normal distribution evidently is not a valid distribution for size, simply because a normal distribution has a negative possible outcomes. The log-normal distribution, of where we have basically, it's a, let me put in my pointer here, is basically you have the same as the normal distribution, you have a mean and standard deviation, except that you express this as a logarithm. So sometimes we add a parameter theta. This parameter tau here is a shift parameter, shifts of the log-normal distribution. It could be many reasons for that. It could be due to the type of sampling. It could be because you want to make something positive, or various other reasons. It's just that's another shift parameter. So you have the 2-parameter or the 3-parameter form. So the log-normal distribution is quite common, and probably you've heard about it. And so you could wonder, why is it that so many variables seem to be log-normally distributed? The answer to that lies in, one of potential answer lies that in what is called a proportional effect. So the proportional effect occurs when we're looking at growth or change in general. And so growth is typically of what we call a proportional form. So imagine I'm growing a crystal. And so you can imagine that I have a certain crystal of certain size, volume, weight at some particular time. And so, and I look to grow this crystal at the next time. So proportionality means that the change in the growth difference, or the difference between something at certain time t and certain time t minus 1, is a function, it's some epsilon multiplied with whatever size that I already have. So we notice that this is not a sum, but a multiplication effect. So if I then rework that a little bit, then you get this equation. Then this proportional effect, right, is that this proportional constant which is then also a function of t, is then this particular form. If I now start growing this, which means I repeat this over time, I go t is 1, 2, 3, 4, 4, etc. Over a long time, then I basically, each time I add this proportional effect, but this proportional effect, of course, is changing as x is changing, then I get this particular sum. So I get the sum over all these epsilons. Now, what is this sum here? So the sum, if you now think about it in more infinitesimal way, a sum of a difference can be written as an integral of dx starting from x0 to xn instead of t is 1 to 0. And then, of course, the integral of dx over x is simply log of x. So that's where the logarithm seems to be occurring. So that means then if I write out log x, I can write it out as the log of what I have initially, the sort of the seed, and then I have these additive terms here where there's these terms epsilon. So because I now add things that are independent of each other, I get again the central limit theorem that says that log of x has to be normally distributed, and so naturally x then is log normally distributed. So this proportional effect can be explaining many phenomena, but not all phenomena. We'll see that there are differences with some other effects. The log-normal distribution is a distribution you're probably very familiar with, in particular related to size distributions. However, there's another distribution that's very commonly observed, and it's called the log-hyperbolic distribution. So why do we call this distribution log-hyperbolic distribution? Well, first of all, let me put my pointer. First of all, we have this seem a very elaborate expression here. Before going into this expression, let's see what happens to the shape of the distribution when we take the log of the density and the log of the variable x. So we're quite used to taking the log of the variable. Here we're also taking the log of the density. If you then look at a log normal distribution, what you will see is you will see this black line here, which is a parabola. So a hyperbolic distribution looks pretty much like the log normal distribution in the center, but looks very different as we go in towards the tails. And so here we see towards the tails that we get that the tails are convergent to some kind of a slope. So this means, evidently, even log-log scale, is that we have a power law type behavior. And so the tails of the log hyperbolic distributions are much fatter, thicker, heavier, let's say, than the log normal distribution. So if we actually write down this expression of this hyperbola, so the hyperbola expression is simply this expression here, where the tails are given by some parameters. And so we can express essentially this distribution with this particular form here. I think the beta has to be a phi. I will check on that. And so what we get is this complicated distribution, but it has essentially four parameters. A parameter mu, which has to do with the mean, and then the other two parameters that are important are these parameters phi and alpha. So these phi and alpha parameters are essentially the indicate the heaviness of the tail, one for the lower tail and one for the upper tail. So we see this parallel. In other words, it tells you what is the slope of this particular line. So the heavier the slope, the thicker the tail, or the larger the slope, the thicker the tail that we're getting. So on this side, this is just a normalization constant. This k here is a Bessel function. So it looks quite complicated. And the resulting of that, of course, is that expressions for the mean and the standard deviation are not analytical, but they can be computed once these four parameters of the distribution have been quantified. So when we're talking about the log-normal distribution and normal distribution, we saw that these distributions can be seen as limit distributions, for example, through the central limit theorem. So there's extension of the central limit theorem that leads to these infinite divisible distribution. I'm going to talk about the specifics of that. But it's also interesting to see the log hyperbolic distribution in the context of mixing of populations, which could be an alternative to the proportional effect. So what do we mean by mixing of populations? You may be familiar with mixing of of densities as a linear combination of other densities with a finite sum. And so those weights are then seen as probabilities of belonging to that particular population that is described by that particular density. So imagine now that we not have a few discrete densities, but we have a mixing of a very large amount of these densities, and these densities are log-normal distributions or log-normal populations. So here we can describe again growth processes. Growth, proportional effect is one way of looking at a growth process. Another way is looking at this mixing of populations. We're going to mix populations essentially by looking at populations where if the mean is larger, then the variance is larger as well. So in other words, in these populations, in these mixtures that we're mixing together, we see a relationship in these mixing distributions where the mean is a linear combination of linear relation to the variance. And so this is not unusual, evidently, is that often we see that when we have in actual populations, when we have larger means, it also means larger variance. So this is an example of what is called heteroscedasticity as compared to homoscedasticity, where the variance is constant. So if we look at that and we look right at the log hyperbolic distribution, or in this case a hyperbolic distribution, if you look at the log, then what we get is this is of course the log normal distribution, and we have here the variance. And so now we integrate out the variance in the sense that we're getting something. We're stating that the variance itself has a distribution, and we're also stating that the distribution, that the variance itself is a linear combination or is a linear function of this mean. So we're introducing new parameters here, which is a and b, and also parameters possibly related to this distribution. Distribution is called inverse Gaussian distribution. I encourage you to look that up. It's not important. It's a bit of a skew distribution. Looks a bit like a beta distribution. And the reason why we take this distribution is that we can then solve this integral, as you will see, as you can understand. So once we have that, solve this integral, we get the expression on the previous page, which was the log hyperbolic distribution. So the log hyperbolic distribution can be seen as a mixing of many log normal populations, and so therefore, as a consequence, has a much heavier tail. All right, so let's see how we can apply this to some data sets. So here we have two data sets. One is the beach deposit in Namibia, and one is a river fluvial deposit in Guinea. So we are expecting well sorting of stones, possibly with the mixing of the populations. And so we tend to expect a log hyperbolic distribution to appear. So what we have, so how do you fit a distribution? There are many techniques, evidently maximum likelihood methods, least square methods. So here we do a simple method, which is commonly done, at least at that time it was, which is through the chi-squared. Basically what we're doing is we're looking at, we have here a sample of say 1,000 stones. We make intervals, classes, and we take those classes and we have the observed frequency, and then we essentially do a fitting and optimization by trying to minimize these differences between the observed and expected frequency. And that is done using an optimization technique that requires, in this case, optimizing or finding 4 parameters and minimizing this difference. And so one way of visualizing already or looking at whether or not this is a log hyperbolic distribution is to make a log-log plot of these frequencies and categories. And so what we get here, these dots are then the observed frequencies, and then the curve is the model distribution. And so we see a pretty good fit here. And this is for the, I think, for the Namibia case. So so that's a nice good fit. The problem of yours here you can see appearing is as you get into this large amount of larger stones here. We're looking at stones, with stones of 400 carat, or at 100 carat, 10 to 100 carat, that we get classes with very, very few observations. And so this is going to hurt us later on, and we'll see that in the next slide, is that the fitting will be highly determined by, well, what is happening here. And of course, your profit is going to be highly determined by what is happening over here, because these smaller stones, while there are many of those, are not as valuable, of course, as these larger stones. So when I was doing this work, I looked a little bit more closely at how well are these classical fitting procedures, maximum likelihood methods, least square methods, chi-square methods, etc. And so what I found is that when you deal with populations that have very heavy tails, and where these heavy tails are really important, that you may get important biases. So just to remind you that the log-hyperbolic distribution has 4 parameters at a mean. It had 2 tail parameters here, a lower tail parameter phi and an upper tail parameter gamma. So this gamma is sort of what we're looking at, right? Because this is a large stone, so we don't care too much about the lower tail. We care a lot about the upper tail. And so if we're going to use classical fitting methods, and we do a simple Monte Carlo study here with 250 stones, 500 stones, 750 stones, then we notice the large amount of biases that are occurring in these fitting procedures, right? So you, for example, you're estimating gamma by almost 14% in terms of bias relative to 2. So, and that has a huge effect if I'm going to then use this distribution, or the estimated values that I get here, to calculate some probability over threshold. For example, what's the probability of having stones more than 10 carat? Or a probability of having stones more than 100 carat, which I have not observed yet in my small samples, but I'm very likely to get. And this is very important, because in these kind of applications, mining applications, we often find that the very few big stones are what makes the profit of the mine. The other question we have is, what about model selection? I fitted a log-normal distribution, or a log-hyperbolic distribution, and what I often get with these kind of skew distribution, I can equally fit the log-normal distribution. It looks equally good. So what do I do now? And the choices that I make between log-normal and log-hyperbolic are quite consequential, since one would invoke a much less heavy tail than the log-hyperbolic, and therefore you would bet on something that has less profit than something has more profit. And so this has important consequences. So the problem with long tails is that they're not easily distinguishable. You could say, well, why don't we just make a normal quantile plot? As you probably remember, a normal quantile plot is where we plot quantiles of the data versus the quantiles of the normal distribution. So here, of course, the log of the data, and these are the quantiles. So, for example, this is all standardized, or this is logarithm. So, and this is the quantiles of the normal distribution. So, if I have a log normal distribution, I expect this straight line. If I take a reasonably heavy-tailed log hyperbolic distribution, I get this line. So yeah, there's a difference. But you can imagine if I have just very few data points here, then this point is going to be either here or there, and so you get this variance problem. Is that one data point is going to determine essentially what I'm trying to do, and that's the difficulty of extreme value statistics. Is that with very few data points, we need to make inference about what happens in the tail. And therefore, the traditional least square methods for fitting, who basically look a lot at the center of the distributions, are not very applicable, and we'll have to find new ways of estimating the tail of that distribution. In the second case study, we are looking here at magnitude and volcano eruptions. So again, we're looking at something of a size. So now we're looking at something that has to do with hazards. And so the understanding of these hazards on a global scale is important, of course, in trying to predict events that are happening. So when it comes down to volcano eruptions, we can start building a global database. And so one of the global databases is this Smithsonian Global Volcanism database that has been compiled. And it's basically a database of eruptions with magnitude greater than 4. So we'll discuss a little bit about what is the definition of magnitude in the next slides. So of course, in creating such database, we can have recent events, let's say possibly over the last few hundred to maybe 1,000 years. There's some record about these volcanoes, but also we can start to look at the rock record and see to what extent we can use that record to complete this database. So the goal at the end would be to model the probability of magnitudes for some, say, extreme events, which we'll see later is m greater than 7. So there are, of course, again, two approaches, or there are two approaches to doing this. One is to start building physical models and understanding the process by which eruptions take place, and possibly from that start to understand what kind of magnitudes can occur at what frequency they can occur. But building such models is quite complicated and relies on understanding a lot of the physics and chemistry that is related to these volcanic eruptions. And so the other viewpoint is just purely statistical and relying on the statistical data to build such predictions. And again, we were looking at extrapolation, meaning extreme value theory and extreme value statistics in order to do so. So here's an overview of what we mean by magnitude of volcano eruptions. So the first one is the this index here. Let me check again down the name. Is the volcanic explosivity index, the VEI, and so it's basically it's a natural scale, or sorry, a scale that's been given. Basically based on a general description and also volumes of tephra. So tephra is the rock fragments and particles that are injected when you have volcano eruptions. So we create a scale for that from non-explosive to, say, very large. So that scale is also based on other things such as the volume of tephra. You see that you get an essentially exponential increase in the volume of tephra, column heights, as well as other qualitative descriptions, or the eruption type. For example, plunian eruptions or commons, or these are eruptions that have to deal with a narrow stream of gas and ash that are violently ejected from a vent to height that could be potentially several miles. So based on that volume, we can actually come up with a magnitude. If we actually measure that volume, we can measure that then, or that mass, and we can look at the combined mass of tephra and lava and make a log10 scale of that. So you can see that would be indeed the case, and then subtract 7 as to get more into a reference zone similar to the VEI. Okay, so what has been done, and I refer to that paper that I cited in the beginning. What had been done is that there was this general database, the GPPD database, and then more data was added to that based on more extensive literature search, where the magnitude was essentially reported, or based on literature where magnitudes were derived. The reference time here is the Holocene, and why we use the Holocene is because it has a lot to do with, or it has mostly to do with glaciation periods. So the last glaciation periods happened somewhat 10,000 years ago, and so what happened before that, of course, is that a lot of the record of these eruptions has been destroyed due to the glaciations. You get into that issue of bias. That information essentially is lost. So we saw here and notice a few things. That first of all, we notice that when we go closer to our time, we see that we have more observations. That's nothing to do with the fact that there are more earthquakes. It's just to do with the fact that essentially we just have more significant observations. What we do notice, luckily, in a sense, is that, yeah, we get a bias in observations in the smaller sizes, but as we grow, we notice that in terms of observation, the large earthquakes, that seems to be quite constant, and that's actually That's actually good news. It's actually the same in the diamond case. We tend to have a biased number of smaller stones. So if you're going to do, again, classical statistics, then this bias will show up in the tail estimation. And so what we don't want to be using is essentially we don't want to essentially base our predictions of the large earthquakes based on just the small earthquakes as well, earthquakes here, volcano eruptions, sorry, because of the issue of having some biased information. Okay, so in summary, first introduction, why we need this extreme value statistics is that first of all, that the distributions of many Earth properties, magnitude, sizes, they are not Gaussian. In fact, they have very long tails, and that these long tails are quite important because they indicate extremes, and these extreme events is often what we need to know, and not just the small events. The classical methods, I've shown a simple Monte Carlo study, but you can do similar and more Monte Carlo studies. That the classical methods of statistical inference do not apply well to these kind of data, simply because they don't focus on the extremes. And so why would you worry about the small stones of the in your sample when you're actually really interested in the extreme? So it seems that we need to come up with something that focuses really on the extreme values and starts from that point of view and not just from a classical central limit point of view. And that's what we'll start with in the next session, which will be on the distribution of maxima.